Okay, so um, let me start by saying what I will do in these lectures. And okay, so I was asked to give a lecture which has to be introductory and somehow addressed to young mathematicians which are beginners in this field. Now, there is something strange about that there are many people I know in this room, and they are no beginners at all. But okay, so I guess that's their problem. You will be bored to death. Okay. So what I'm going to do is I would like to start with a quick introduction to the plateau problem and minimal surfaces. And so in this quick introduction, we should cover just the lecture of today. I would just like to mention what are the basic tools, at least in the smooth case, so the area formula, and mention the basic computation you have to know, that is compute the first variation of the area and prove that a surface with minimal area has zero mean curvature. Okay, so at least in the smooth setting. So that's basics, and I'm not somehow interested in any sophisticated notion of surface or whatever. Okay, so that's what I would like to start with today, and then I will mention somehow, okay, what is the main mathematical problem in the area of minimal surfaces, is, if you want, is existence. That is, okay, once you have a regular minimal surfaces, well, by minimal surfaces I mean now area minimizing surface, you can show many things, but the problem is, why should there exist a surface with a minimal area with prescribed boundary? Okay, and so this problem has many answers, and perhaps none of this is the answer. And so I will spend a little bit of time to review what are the different approaches. And but then in the next lectures I will be devoted to the analysis of one of these approach, and is the one based on finite perimeter sets. Okay, so that's just one possible way to approach the problem of minimal surfaces, and that's what I will describe in detail. Okay, and this will take the next two lectures and probably also a piece of the following one. So what I will do essentially is a lot of preparatory work explaining what are rectifiable sets, what are finite perimeter sets, what are the properties of finite perimeter sets. Some of them are easy, some of them are a little bit harder, and so I plan to cover more or less the basics. And then I will conclude with few existence results, so somehow completing the tour, and maybe mention a couple of other things if time allows. That is, maybe talk a little bit about regularity of these minimal objects we have produced, and spend some time on the so-called Modica-Mortola theorem, which is the approximation of the minimal area problem with other with somehow elliptic problems. So, which this should have some interface also with the course of Yoshiro Tonegawa. Okay, so let me start with the plateau problem. Okay, as I said, plateau problem is simply the following. Find, let's say in dimension for surfaces, is really find well, let's say find the surface with minimal area spanning a given curve. Okay, and okay, so that's how it is stated. Let's say what find means usually is well, prove existence or something like that. Okay. Surface now in the original version of the problem is essentially two-dimensional surface spanning a given curve. A curve is a curve, okay, and the ambient space could be R3, where that makes sense, or if you want some reasonable space, a Riemannian manifold where you have notion like area and so on. Okay, but of course you can extend this to higher dimension, that is not only consider surfaces, I mean two-dimensional surfaces, but objects with higher dimension. So find the d-dimensional surface with minimal d-dimensional volume spanning a given d minus 1 dimensional boundary. Okay, well, somehow to fix it, I will call the surface, usually I will call it sigma, and the boundary gamma. And why not? I will use the same terminology here. Okay, and okay, what is the volume? Now it's not important, but I will often refer to the d-dimensional volume as area as well. Okay, simply because it's quicker. Okay, so as you can see, well, this problem is not really a precise problem. And it's not precise in that I didn't specify, well, essentially, what do I mean by surface? What do I mean by area? And what do I mean by spanning? Let's say the fact is that there are infinitely many variants of this problem. And they vary, and they vary exactly in the fact that the class of admissible object, that is, what are the admissible surfaces, varies, depends on your problem. What does it mean that a surface spans a curve also varies. That depends on your setting. And actually, there is not even an agreement on what area is. That is, well, for those who know, when you work in currents, you minimize the mass, and the mass is not exactly the area. So this is not really a precise problem, and depending on the framework you choose, you get different answer. And the framework, in some sense, depends on what you really want to do. So what is the problem inspiring? So you might come to minimal area problems because of applied problems. And in some sense, the problem you start from defines exactly what are the surfaces, what are the area, what is the area, and what spanning means. Okay? So by the way, the name comes, Plateau was a Belgian physicist 2 centuries ago who studied soap films, and which are example of surfaces of minimal area. Okay, I doubt he stated this problem because, you know, he was studying soap films; they existed. So I don't think he was interested at all in existence. That was obvious, right? And okay, but it's called the Plateau problem, nevertheless. Okay, so let me see. What is there is one fact that, in some sense, I would like to come to very quickly, and is the following fact. So, if sigma minimizes area, then the mean curvature of sigma is 0. Okay, so this is simply a way of saying that the equation h equals 0 is the Euler-Lagrange equation of the area functional. Okay, so minimizers of the area functional must satisfy this Euler-Lagrange equation. Okay, and I guess the parallel we are all familiar with is that the minimizers of the Dirichlet energy satisfies the Laplace equation Laplacian equals 0. And this is in the very same spirit. So this I would like to explain in detail today. And of course, I will assume that sigma is as regular as we need to do the computation. So we are not doing any weak theory today. Let me just remind you that because of this reason, surfaces with zero mean curvature are usually called minimal surfaces. Okay, so minimal surfaces means not that they minimize area, but they are critical points of the area functional. Okay, so this is the minimal surface equation. So, but in this lecture, I will always talk about surfaces that minimize the area. I will try to call them area minimizing surfaces, but at some moment, I'm sure I will say minimal surfaces. But common terminology, minimal surfaces are critical points of the area function, not minimizers, okay? Very good. Okay, so what are the basic tools we need? No. How do I move this here? Then I will have to find out how to send the other one up, but that's for later. Okay, so area. Okay, now really, as I said, this is going to be a basic course, so I will say what area is. Well, actually, this will be the d-dimensional volume. Which, to be precise, is the d-dimensional Hausdorff measure. Okay, but often I will write also something like this, if it's clear that we are talking about the area. Okay, and what is the d-dimensional Hausdorff measure? Okay, let's point out. Now, this just because it will occur also in other lectures, let's just go through the definition. The fact is that as long as you talk about regular surfaces, whatever notion you have of area of d-dimensional volume, it's fine, okay? So there is nothing particularly relevant about Hausdorff measure in the context of smooth surfaces, okay? But let's so you could replace that with your favorite notion of volume. So the definition, very quickly. So you have a set E in Rn, a dimension D in 0 plus infinity, and the delta, parameter delta larger than 0. These are given. Then you define the Hausdorff pre-measure, d-dimensional pre-measure of E in the following way. You take all possible covers of E, countable covers of the set E with other sets, EI, and you take the diameter of these sets, EI, take the power D of this, sum over all I, and now you optimize among all possible covers. So you take the infimum among all countable okay? And actually, there is a renormalization constant here, which is relevant, and this is so renormalization constant, and I will come to it in a second. Okay. Okay. So this is a Hausdorff pre-measure, and then you have HD, the Hausdorff measure. So the dimensional Hausdorff measure of E is the following, is the limit of this quantity as delta goes to 0, which is actually a supremum because this quantity is increasing as delta decreases. It didn't appear in the definition, right? So, something strange. Among all countable covers, such that the diameter of EI is less or equal to delta for every I. So I cover with set EI whose diameter does not exceed delta, and that's the definition. Okay. Then I take the infimum. Renormalized constant will come into will be clarified in a second, and then I take the limit as delta goes to 0, which is a supremum. Okay, it's clear it is a supremum because of this position. If you decrease delta, then the class of admissible cover gets smaller and smaller, and therefore this infimum is larger and larger. Okay, so it's clearly, this quantity is clearly increasing as delta decreases. Okay, so that will be our notion of d-dimensional measure. A few comments. Well, the first is technical. Is it a measure? What do I mean by measure? This definition, oh, by the way, first, comment 0. I don't need to be in Rn. Any metric space will be okay. Okay, because the only things I need is the notion of diameter, and diameter I need a distance to define, but that's it. So it's actually a definition that works in metric spaces. Then the first is that, well, when I say measure, there is something you have to be careful, and this will be the only time I will spend some words on these issues about measurability and so on. What happened is we are defining this quantity for every set E. There is no restriction on the set E. So what do you get in the end is not a measure in the sense of a sigma additive function, but a sigma subadditive function. So these are outer measures, as they called. Our outer measure that is their sigma subadditive, which means simply that if you take the union, countable union, the measure of a countable union will be less or equal than the sum of the measures. But equality may not hold even if you assume that these sets are disjoint. Okay, so sigma subadditive means that you don't necessarily have equality here when the sets are disjoint. Okay, so but that's not what we expect usually from measure. We don't like to work with measure with this property. We really would like to have sigma additive measure, but this is just a technical fact. Now there is one. The first fact is that if you look at this measure, and it is additive provided that on a couple of sets if they are distant enough. So you have this inequality, this equality. if you take two sets which are distant enough, then the measure of the union is, so not just this joint, the measure of the union is the sum of the measure. If the distance between these two sets is at least delta. So what I mean is that these are my two sets, and I'm asking that the distance is at least delta. Then you clearly see that whatever cover you have of the union, you can split. Okay, since you are covering with set with diameter at most delta, any set in the cover of the union with either intersect E1 or intersect E2, which means that you can split that cover into the union of two covers, one for E1, one for E2, and that's the basic fact that you need to show that here you have equality and not just the inequality. Okay? And now a consequence of this, and that's exactly why in the definition of Hausdorff measure you take the limit as delta goes to 0, is that if you look at Hausdorff measure, then you have this equality if the distance is positive. Okay? Because if you want, you are taking the limit as delta goes to 0. And now it's a theorem by Carathéodory which says, well, then our measure is a sigma additive on Borel sets. Okay, let's write it here. Then HD is sigma additive on Borel sets. And as far as I'm concerned, I will only consider Borel sets from now on. I will never consider other sets than that. For our purposes, they are perfectly enough. And okay, there are tricks in general. If you really do hard proofs in geometric measure theory, sometimes you take projection of sets, and that's bad. Borelianity is not preserved by under projection, but this is not something we have to worry about. Okay, so it's not true that this choice is hassle-free, but we will never see the problems in this lecture. Okay, so Borel sets is what we are using, and there, this is a measure. Okay, so we don't have to worry about this. Now, how do I send this up? That's easy. Okay. Okay. So further remarks? Why this measure, Hausdorff measure, is called d-dimensional? Because it scales in a d-dimensional way. So what you have is that if you take a set and you enlarge it by a factor lambda, then the measure will enlarge by a factor lambda to the d. And so that's why we call it d-dimensional, okay? Because that's what you expect from a d-dimensional measure. Okay, the other reason why this is called d-dimensional is that actually it agrees with the Lebesgue measure on Rn. So the Lebesgue measure on Rn, on Rd, sorry, agrees with the Hausdorff measure. Actually, it also agrees with the Hausdorff pre-measures. So that's the other reason. Okay, so this is a generalization, if you want, of the usual measure, d-dimensional measure on Rd. Let me just mention all what I'm stating so far is everything is trivial. This identity is not that obvious, and one of the reasons is that I don't know what definition of Lebesgue measure you were given, but the standard one involves rectangles. And rectangles depends on the choice of axis, while Hausdorff measure does not depend on the choice of axis. So there is actually something not completely trivial in this identity because, well, yes, the two definitions are similar, but not exactly the same, right? When you define Lebesgue measure, you are not really covering with any sets, you are calling with rectangles, and you don't take the diameter to the power d, but the volume. So not quite the same. So this is not a completely trivial statement, and it depends on the choice of the normalization constant. So because, well, that's not just the reason, but because of the choice of the normalization constant alpha d, which has to be just the volume of the unit ball in Rd. Of unit ball. Now, of course, if d is not integer, it's not clear what that means. And it's not that important, because if d is not integer, you don't have a reference measures like Lebesgue measures, so you don't care. In fact, if you take books on geometric measure theory like Falconer's books or Mattila's books, where they are not particularly concerned with surfaces, then there is no renormalization constant at all around, because that's not the point. If you're interested in fractal dimension and so on, then you don't put a renormalization constant in the definition, okay? Because you don't need it, because it doesn't make sense. It makes sense if you want to connect this notion to area and to the usual notion of area. Okay. Well, here you see that delta doesn't matter. You could have taken it in the definition. So why take delta goes take the limit as delta goes to 0 in the definition of out of measure if here we get exactly the same whether delta goes to 0 or not? Well, of course, then in Rn, in Rd, you don't need to take delta that goes to 0. You could just take the definition up there without any restriction on the diameter. That would give you Lebesgue measure as well. But you have to take delta. This limit is needed. Not in Rd, but the simplest example is that, okay, take a spiral with infinite length but bounded. Then, of course, if you compute any of these measures, you get a finite number because you can cover that object with finitely many balls of radius delta. But, of course, the length has to be infinite. Okay, so in order to have that h1 of this spiral is infinity. So you want this from length, but if you compute h1 of delta, that's always finite, okay, because of obvious covering reasons. So you really need to take this delta to 0. I mean, you can't have a definition that skips this part. This might happen to. Okay, let me just add this remark. In the definition we cover with sets, does it matter which kind of sets we use? Not too much answer. So the definition. So the sets EE, EI in the cover. So in the definition. Don't need to be any sets. If you take closed sets, you get the same number. Of course, closing a set doesn't increase the diameter. If you take open sets, you get the same number. Well, because if you enlarge a little bit a set, you can make it open by increasing the diameter just by a little. You can make them convex, because convexifying a set doesn't increase the diameter. You can't make them balls. That you cannot. Okay. So the sets can be taken closed, or open, or convex, open, close, open and convex also, or close and convex as well, not balls. Because that's not true, it is not true that a set of diameter d is contained in a ball of diameter d. Okay, triangle provides the counterexample. Okay, that's not important, but knowing that you can take open sets might be useful in doing certain computation because may reduce to finite covers by compactness, for instance. Okay. Now, well, associated to all this, there is a notion of Hausdorff dimension, but that's not so important for this course, so I will not be entering into this. Well, very quickly, what is the point? If you take two-dimension d and d prime less than d, then you have some obvious results. That is that if h of d of a set is finite, well, then h d prime of E is equal to 0. I mean, in some sense, if a set has finite length, is a curve, then its area must be 0, right? Okay, so that's what you expect. You can prove it in general, and it's really easy. Vice versa, if you have that h d prime of E is finite, if a set has finite area, then it's positive. If a set has positive area, then its length must be infinite. Okay, and so this you prove in general. Okay, and this tells you that in some sense, if you look at what happens to a Hausdorff measure as d varies, it will be plus infinity till a certain point, certain critical d, where it changes and goes to 0. And so this critical d you call Hausdorff dimension of the set. Okay. So this is the definition. The Hausdorff dimension of a set E is either the supremum of the d such that the Hausdorff measure is plus infinity, or the infimum of the d prime such that h d prime of E is 0. And these two numbers are the same, and somehow this separation d is the Hausdorff dimension, which doesn't imply that if you take d equal to the Hausdorff dimension, you get a finite number. Okay, so that's not that, but still is the dimension. Both notion of Hausdorff measure and Hausdorff dimension are metric. So they behave nicely under Lipschitz transformation. They don't behave nicely under homomorphism. In particular, there is a relation between the topological notion of dimension and Hausdorff dimension, but they are by no means equal. Okay, at least for the obvious reason that one is invariant under homomorphism and the other isn't. Okay. So this is it for Hausdorff. Let me go to the first tool we really use, that being the area formula. Okay, so far this was very general discussion, and in some sense you can forget all of it without any harm done. But here comes something that we really use. So how to compute the Hausdorff measure of a set which is reasonably regular, whatever that means. And somehow here is the main tool, because of course you can define these measures, but you don't really want to compute infimum over covers and then supremum. Okay, so that's the area formula. Well, let's put. So the answer is the area formula which says the following. So let's say that F is a map from Rd into Rn of class C1 and injective. Okay, and then you take the image according to F of some set E in Rd, and you ask, okay, what is the Hausdorff dimension of the image? Okay, so the idea should be that, okay, this is a d-dimensional object. It lives in Rd, so the image should be a d-dimensional object. And so the question is, what is this? Okay, and the area formula gives you exactly a way of computing this. So, well, you can guess it must be something like the integral over E with respect to the usual Lebesgue measure. But what you integrate has to be, okay, that's the point. You integrate the Jacobian of f of x. And the point is how you define this. So what is the correct definition of that? Okay. Well, okay, let me give the definition which should make clear why the formula is the correct one, but is not the way you compute really this number. Okay, so this essentially what you do, you look at the derivative of f at x. If that's not of rank d, then this scaling factor here has to be 0. So this is 0 if the rank of the derivative is 0. Okay, so to be precise, I use this notation to denote the differential of f at x. That is the derivative intended as a linear map, in this case from Rd to Rn. When I want to talk about the matrix associated to that, so the Jacobian matrix or whatever it's called, then I will use the nabla. Okay, so nabla stands for this stands for the matrix, and this stands for the linear map represented by that matrix, or vice versa, depends on the way you are being taught. Okay, so this is the linear map, and this is the matrix. Okay, it's the same anyhow, the notion of so the rank has to this Jacobian is 0. Otherwise, what do you do? Well, if it's not rank 0, then what you do is take the determinant of this linear map. Well, that's not a very clear notion. What do we do exactly is, okay, if we are in this situation where this rank is d, sorry, why 0? Then the image of this linear map, well, somehow the tangent space to the set in that image point will be d-dimensional. Then we can choose an orthonormal basis of the image of this space. Once we have chosen an orthonormal basis of this, so we choose orthonormal basis of the image. Okay. Then we can represent this linear map by matrix, but now, since we have chosen an orthonormal basis, well, in Rd we take the standard orthonormal basis. In this space, we take this new orthonormal basis. Now, this becomes a linear map from Rd to a d-dimensional space. We have two orthonormal bases. We can associate a matrix to this one. So associate to the f of x a matrix M, n, and now you simply say, okay, what is this determinant? Is the determinant of that matrix, okay? Then set I insist on putting the absolute value because the sign in this procedure is not well defined. What does it mean? If you change the basis here, you will get the same, okay, I mean, basically you will change the matrix here by multiplication with an orthonormal matrix. So the determinant will remain the same up to a sign. So that's why you can only define the modulus, okay? The absolute value of this determinant. It doesn't make sense unless you have an orientation blah, 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 which is not the case here. Okay, so you can only define this, and this is what you put here, okay? So you view this as a linear map from Rn, Rd to a d-dimensional space, not an n-dimensional space anymore. Then you can compute determinants. Basically, that's what I'm saying, okay? And that's what I put there. Now, let me say, okay, this is why this is the right things to put. Well, if you want, because certainly if here n is equal to d, so if we have a map from Rd to Rd, well, this becomes exactly the usual formula for the change of variable in integrals, okay, the one that is done in calculus courses. That's exactly because we put here the determinant of the gradient, modulus of the determinant of the Jacobian, sorry, okay? So this is the usual formula in case of change of variable in integrals as long as this is n is equal to d. So that tells us that this must be the right things to put there, okay? But of course, if you want to compute this quantity, I must say this is really bad, and the reason it's really bad is that you would have to choose a basis of this linear space in order to make the computation, so you don't want to start with this, okay, as a formula. So in fact, now I will give you formulas that can be used in computation. So this cannot really be used, but the following one can be really used in computation, and this is the following: square root of the determinant. Now you take really the gradient matrix, okay, so that's usual matrix, but this is n times d matrix. So you can't take the determinant of this, but if you multiply by its adjoint, it becomes a d by d matrix. You can compute the determinant, and you get the same as that. Okay, so n by d matrix, d by n matrix is the adjoint transpose matrix. Take the product as d by d. The determinant is, the product is not only d by d, but also positive definite, symmetric. So the determinant is positive, you can take square root. And it happens to be the same as this. So the difference is clear, right? You can compute. It may be boring, but you don't have to choose a basis. It's just a mechanical computation. And there is another identity which is somehow useful to know, which is, well, that another way of computing this is the following. You take all minors m. So this is an n times d matrix. It contains several d times d minors, m. You take the determinant of each one of this. You square it, sum, and you sum over all minors. D times d minor of the gradient. Okay? Actually, it's interesting. This is easy, linear algebra. This is not so easy, So this is a consequence of the so-called Binet formula, or generalized Binet formula, or whatever. Let me see why this is easy. Well, why this is true. Okay, why the first identity is true? How do you obtain that? Okay, first identity. Well, of course, let's go back to the, well, definition. Okay, the square of this, no, I don't need that, sorry. This is the determinant of the matrix N defined here, okay? Now, this determinant is certainly equal to the square root of the determinant of N transpose N, simply because this is the product of the determinants, they are equal, so you get the square of the determinant of N. Now, the point is that N can be obtained by the gradient matrix just by multiplying by the change of basis. So N use a change of basis matrix, the suitable change of basis matrix, and you get R just by taking okay, and then this becomes the determinant of gradient F transpose R gradient of F. And now this is not the identity, though very close to that, because since the basis is orthonormal, the vectors of this are orthonormal vector, but that matrix here is an n by n matrix, so it represents a linear map on Rn, which is just the projection, orthogonal projection on the space, on the image of the Jacobian. So this is a projection matrix, but it's the projection on the image of this matrix, well, the image of this matrix, so the image of the linear map associated to this matrix. So this is a projection matrix, but when I apply to this, nothing changes, it's like the identity. So this together is equal to gradient of F. Okay? So then I'm finished, okay? I've obtained the main one. And the other one, okay, as I said, that's Binet formula. I don't know any proof of it which is not a bunch of computation or multilinear algebra, actually. So I like the proof with multilinear algebra, but I'm not giving it here. There's a nice geometric interpretation, the second formula over there, but I'm not giving to it. So Binet formula is the following, okay? Let's say the easy version is this. If you have an n d by n matrix, then the determinant of this product is the sum of the determinant of the minor squared. Okay. In fact, the real statement A and A are not the same. So here is a B, here is an A, but of course here you have to do something a bit more complicated. So, but this is the linear algebra formula that you might want to know. Okay. Good. Okay. Just a few remarks on the area formula. So, by the way, if you look in the literature, usually you will find this as the formula for the area, fine, but the definition of Jacobian will be probably directly the second line here, okay? So maybe they will skip the first line because it's just cumbersome if you want, okay? Why to give the first definition? The only reason to give the first definition is that, as I said, it gives you a good reason why this formula should be the correct one. So let me give some remarks. Well, let's start from the easy cases. So if D is equal to and n is equal 3, so if we have a map from two-dimensional space from R2 to R3, okay, then this Jacobian, this complicated formula, may have some formula that you have been familiar since the time of calculus, which is the following. So how do you compute the area of a surface? Is through the parametrization. You take the partial derivatives, parametrization f, you take the partial derivatives of f, take the vector product, are two vectors, take the vector product, take the modulus, integrate, okay? It simply means that this is given by these two vectors. This is the usual vector product in R3. And I guess this is a formula that has already been seen. Okay, standard calculus. Well, it actually can be generalized to the general case, but that requires the notion of external product and k vector. So for those who knows, I just recall it. In general, you take the same as before. You take all the partial derivative. You take their product. So these are vector in Rn. You take their product in the sense of exterior product of vectors, whatever that is. We will not use it as far as possible. You get what is called usually a k vector, a d vector. You take the modulus, and that's the Jacobian. So, but this formula, we will use it quickly, so that's somehow keep in mind, okay? The point is that this product in, this product in R3 gives you a vector in R3. If you multiply two of them, two vectors in R3, in this way, you get the usual vector product in R3. But if you go to general dimension and codimension, these are no longer vectors, okay? Are k vectors or d vectors or whatever. Okay. I'm not interested now in this. I will try not to use it at all. The other formula which you might be familiar with, and which is implied by this, is the formula for the area of the graph of a function. So if you take function from Rd to R, you take its graph, then the formula is the following. Okay, what am I saying? That, okay, you can parameterize the graph by a map f, simply the one that takes x into x comma g of x. You can apply, so the image of, sorry, not Rd, that's not a good idea. Subset of Rd. The image of E, according to this map here, is exactly the graph. And now if you apply that formula over there, and you compute the Jacobian, you find out, again, you recover the familiar formula. Sorry. Okay, but this formula is no longer true if you consider maps G with values in a higher dimension than that, okay? And the reason essentially is the following. If you look at the gradient of f, well, the gradient of f is the identity matrix times the gradient of G down here. Now if you look at n by n, d by d minors of this will be identity. Essentially you get the identity times one of the component of Gi. So when you the determinant of the d by d minors are exactly the absolute values of the components of this vector. You square them, you sum them, you get the absolute value of that, except for one minor, which is the first one, which gives you 1 as a determinant. So this is the determinant of the identity of this minor, and if you write this as sum of the components square are the determinant of the other minors, okay? But of course, if you have a map with values, G takes values in R k larger than k, the formula gets more complicated. Just to make it sure, this is no longer the formula for the area. This is only for graphs of codimension 1, okay? Maybe I'm insulting you by making this precise, but it happened to me in the past that people had some strange misconception about the validity of this formula. So just wanted to make it sure. No insult meant. Very well. How do you prove the formula, the area formula? Well, I'm not going to prove it, of course. I'm trying to convince you how you should go to prove it, which way you should go to prove it. Well, okay, so the formula, that one, which maybe I should have of this one, should have put. Okay, the area formula is clearly correct. If n equals d. That's what I said before, because this is the usual formula for the change of variable in integrals, okay, which involves the determinant of the gradient. And that's why I decided to define the Jacobian that way, because that gives you immediately the usual change of variable formula, okay? So that's the easy part. But then it is also clearly correct if the image of f is contained in an n-dimensional subspace of Rn. Is clearly correct if case 1 n equal d equal n, and second if the image of f is contained in v equal d dimensional subspace of Rn, because we said that the dimensional Hausdorff measure on this will be essentially the Lebesgue measure, okay? So then for the same reason, you reduce to this case. And now the key point, I'm not going through the details, of course, is that you prove the general case by approximation. So what does it mean? It means that this will be the image of f, and then you approximate it with linear, okay? With linear images. Okay, as I said, I'm not going through the details, but essentially what is the idea? The idea is that so you modify your map f so that its image is linear by, for instance, you compose the projection of this surface on its tangent plane. Then the formula is correct. And then the only things you want to know, the only things you need in the proof is that actually, since the projection that takes this curved part of the image into this flat plane is almost an isometry, you just want to know that almost isometries almost preserve Hausdorff measure. That's the only things you need. So what you need, technical lemma, is that, well, it's not a lemma, it's a remark actually, it's really trivial. So that if you have a map which is almost an isometry, that is well, which I will not call, if G goes from R, doesn't matter, from 2 metric space, okay? If the Lipschitz constant of G is less than 1 plus epsilon, and the Lipschitz constant of the inverse is also less than 1 plus epsilon, which is saying that this is very close to be an isometry up to a factor epsilon, then the Hausdorff dimension of G of a set E is less than 1 plus epsilon, the Hausdorff measure of E times power D. And it's larger than 1 over 1 plus epsilon to the D. Okay? So that's what you need. Almost isometries almost preserve Hausdorff measure. And this inequality only uses this, and it's trivial. If you take the definition of Hausdorff measure, it's immediate, okay? Actually, it holds that if this is the Lipschitz constant L, here you would put L to the D. Okay, so that's absolutely comes from the definition of Hausdorff dimension. It doesn't contain any complicated things. So this is the basic fact. If you have this, you prove the area formula in general. What do you notice out of this? And this is the last remark for this, and then we take a break. What we notice out of this is that as long as you are talking about objects that can be parametrized, the area formula works to compute the Hausdorff measures, but in some sense it will work for any notion of d-dimensional measure you use, as long as this notion of d-dimensional measure has the usual reasonable properties. That is, it will be invariant by translation and rotation, it will be the Lebesgue measure on planes, and has the property that a small perturbation, that it is almost preserved by almost isometries. What does that mean? Well, whatever notion of d-dimensional measure you can actually imagine will probably have all these properties. This means that for these sets that can be parametrized by maps, the area formula works whatever is the notion of d-dimensional measure you use, as long as it's reasonable. This also means in some sense that for these sets, all the different possible notion of d-dimensional measures actually boils down to the same object. Okay? So of course, then why Hausdorff measures? Tradition. Okay? It's no absolutely. You could have replaced Hausdorff measure by anything else which has the same basic properties, it works fine. So spherical Hausdorff measure, other complicated integral geometric measure, they all produce a d-dimensional measures which is the same for objects that can be parameterized because you prove the area formula in the same way. Okay? So this is telling us that as long as we are interested in sets that can be parameterized in some sense, it doesn't matter whether we use Hausdorff measure or anything else. Okay? But of course, if you go on sets which are really wild, like fractals, then it's no longer true. Okay? There you see a difference between the different notion of measures you use. But we don't. Okay? Not in this course, and I don't think in this school. Maybe in Tatiana Toro's courses. Okay? There could be something. Okay. Let's start over again. Okay, this is the area formula. I said variance, okay, very quickly about this. So in some sense, it's your duty to imagine all possible variants of it. The first one is, okay, I said injective here. What does it change if it's not injective? Well, it changes in the sense that here you will have to count the multiplicity of f. Okay. If f is not injective, so in fact, this is the area formula, right, without assuming injectivity. Then what you really have is that, so you have an identity like this. The right-hand side is the same as before, but in the left-hand side, you have to count the multiplicity of f. So points here must be counted twice if the multiplicity is twice and so on. So what you do, you integrate So you look at every point in the space, you look at how many pre-images it has in E, and you integrate this number. With respect now, let's be precise, will be Hausdorff measure. Okay, so this is the formula. And of course, okay, well, it turns out that if f is injected, this is 1 if the point is in the image of E and 0 otherwise, so you get exactly this formula here. Okay, so here you could put Rn, doesn't matter, or the image of f of E is the same. Well, maybe it sounds less wrong if I put this. Okay, but it's the same. So this is the first modification you might want. The second, okay, let's say you have to integrate a function, not just to compute the area of the image. You can imagine what the result is. So here is the most general one. Let's say you want to integrate a function here. You want to make it look like a change of variable formula. So let's say you integrate a function here. And here you will get an integral which involves multiplicity, or okay, which is the same. This is a function of y, and you integrate this. And again, let's put this just to make it look more less wrong. Okay, so that holds true for every Borel positive function. Positive just to avoid troubles with integrability. Okay, of course you don't need positivity if the integrals exist. Okay. The other things that I want to attract your attention here is that we are talking about computing the measure of the image of a set parameterized by a map. And okay, the map is F, and the parameterization domain is a subset of Rd. But of course, it doesn't need to be a subset of Rd. That could be also a subset of a surface itself, of a Riemannian manifold. It doesn't matter too much. But you have to be a bit careful about this formula about the Jacobian. So the original definition of the Jacobian, this one, this somehow makes sense. Doesn't require, I mean, as long as you have a Riemannian structure. But of course, these formulas here are a bit more specific, so you might have to adapt them a little bit, but it's still true. So it can be also F from a manifold into another manifold. One d-dimensional and the other n-dimensional. It works as well. Of course, this must be Riemannian manifold. I mean, all these concepts are metric, right? If you don't put a metric, it doesn't make sense. Okay. And now, as I said at the beginning, one of the key points to keep in mind about minimal surfaces, well, no, sorry, area minimizing surfaces, that they have zero mean curvature. And I would like to show that. Okay, so it's a basic computation. I will do it in the smooth case, but that's something that it's important. So essentially now I will do what is called the first variation of the area. It's a formula. From now on, everything will be as smooth as needed. Okay. So what is it that I want to do? Okay, so keep in mind the purpose is to show that minimal surfaces have zero mean curvature. And okay, take some preparation. So the first thing is I need to define a flow. Be a smooth flow in Rn. Or what do I need by a flow? I mean a map of diffeomorphism which is smooth in both variables, t, the parameter t and the x variable. So phi t is differ, and at time t equals 0, sorry, defined for all t in an interval, and at t equals 0 you have the identity. Okay, so that's what is a flow. And now we can talk about the initial velocity of a flow. I mean, if I take a fixed point x and I let it move, let vary t, so I take phi t of x, this point will be moving, it will have an initial velocity. Okay, so initial velocity field v of x is simply defined. You take a point x, you let it move from its initial position according to this flow, you take the derivative with respect to t, and you compute this derivative at t equals 0. Okay, so that's the initial velocity, and it's a vector field, okay? And now, given a set sigma in Rn, we simply write sigma t for its image according to this flow. Okay, and the question is, what can we say about the measure, d-dimensional measure of this? So we would like to say something in particular, we are interested in this. We want to compute the measure of this perturbed set. So we take a set sigma, we perturb it using the flow. We want to compute the measure, and then we are not that, well, this is very general, asking how much is this. We are interested into the derivative of this at time t equals 0. So we take, thinking of an infinitesimal perturbation of sigma, and we want to understand what happens to the area. Okay, so we want to derive this and compute t equals 0. So the question is, find a formula for this. Okay, so something you can compute, and fortunately enough, there is a formula. Okay, but I will not give the general answer. I will restrict myself to a very specific case, that is where the dimension d, well, first, there is a formula only if d is integer, okay? There is no such a thing if d is not integer. And sigma is a surface. Okay, so I will assume sigma is a surface, d-dimensional surface, of class C1, if you just want to know, but this will come out from regular enough. D is equal n minus 1. So talking about codimension 1 surfaces, okay, I will do just this computation. There is a general formula for every d integer though, but not, okay, I mean, if you are considering sets which are not surfaces, fractal sets, there exists no such a formula. Okay, there is simply this object cannot be computed, presumably doesn't even exist. It would be too nice if it existed. Okay. So, and the formula is the following. Then, this quantity t equals 0 is equal to the integral over the sigma just of the tangential divergence of the vector field V. Okay. Now, since I'm in the smooth case, everything is clear. Please, I will drop the indication of the measure, okay, from now on. I mean, it's not so important. So I will not write the measure every time. Okay, so this is the, what is this? Is the tangential divergence of V. Well, tangential with respect to what? With respect to sigma, okay. How do you compute it? Well, you take, at a point x, this divergence is computed in the usual way. Well, almost the usual way. That is, you take an orthonormal basis of the tangent space to sigma at that point. You take the partial derivatives, and then you take the eth derivative of the eth component of the vector field and sum them up. Okay, so, well, let's be precise. Sum, okay, I take the derivative of V. Let me, please, allow me to write it as a linear map. I apply it to every vector E of the basis. This way I get a vector again. Okay, and then I take the eth component of this vector, that is scalar product. Okay, and E runs from 1 to D, and EI is an orthonormal basis of the tangent space of sigma at x. Okay, and this divergence doesn't depend on the choice of the basis. Well, the same problem, of course, occurs with the divergence in Rn. Okay, it's, as it is defined, it depends on the choice of the canonical basis, but it doesn't. Okay, so this is the tangential divergence. And this simply says, so this formula says that this derivative can be computed and depends only, well, as it should be guessable, by the initial velocity of the flow, okay? And, okay, let me prove it, because as I said, at least something I would like to prove today, and this seems to be the most important thing. Okay, proof. No, first let me see if there are remarks to be. No, no remarks. Proof. Okay, well, how do we compute this area? Using the area formula. That's the only things we can do. Okay, so we start from phi of t. And now we do something simple. Well, what is phi of t of x? I take the Taylor expansion at time 0. It's phi 0 of x, which is x, plus linear term of the Taylor expansion is the velocity times t, plus a term of order 2 or more. Okay, so certainly, this, in some sense, this formula has to be correct. Okay? And now I go and I want to compute, so I want to apply this formula with phi t instead of that and sigma instead of E, and I have to compute the Jacobian. Okay, so now notice, however, that I'm considering phi t as maps from sigma into sigma t. Okay, so I want to apply the area formula, but I shouldn't think about phi t as maps from, they are defined on Rn. But I don't think of them as maps defined on Rn. I think of them as maps defined on on sigma. So when I think about computing the Jacobian, there is a problem I mentioned before, that I'm considering a map from a surface to another surface or whatever, but the Jacobian is not given by this formula because I'm restricting my map to a surface. Okay, but it's something like that. So from now on, phi t is a map from sigma to sigma t, or let's say from to Rn. That's not important, but the domain is this one. Okay, so I want the area formula for maps defined on a surface. So what should I do? Well, let me write first the derivative as a linear map. Derivative at x is a linear map from what? From the tangent to Rn. And what is it? Is, well, let's write it formally. It's dx, identity map, plus t dv of x. Well, whatever comes here will be order of t squared. But now I want to apply this formula here. So I want to take a gradient out of it, a matrix. And to take a matrix, I must choose a basis in the tangent of this space and the basis here. Okay, so choose basis of tangent. And then the basis I use here is the same basis plus the normal. Okay, so I don't use the canonical basis of Rn. I use the basis given by the one of the tangent plus the normal. Use E1 ED plus the normal as basis of Rn. Okay, once I've chosen this basis, somehow writing this in terms of matrices somehow comes easy, because here I will get the identity map matrix. Well, not exactly. The identity matrix plus a line 0 in the bottom. This goes here, and J is this one. So it must be an n times d, and d plus 1 times d matrix, as the d times d identity matrix plus a 0. And then whatever matrix come from this. Okay, fine. Now we compute this. Well, I'm interested in keeping the term of order 0, the term of order t, and then the rest will be big O of t squared. So what I get, if I multiply that matrix here by its transpose, I get jtj, term of order 0, plus term of order t will be jt times the gradient of v at x, plus its transpose. Sorry, this is not t, is star. And the rest will be of order 2 or more. But this is the d by d identity matrix, okay? And what is this? Well, that's its transpose, but this is just, you take the gradient of v, which is a d plus 1 times d matrix, and just delete the last line. Okay? So this will be, let's denote it. It's not really the tangential gradient, but let's call this m, right. I call this m, and this will be therefore m transpose. Okay, then I take the determinant of this. Now I take the Taylor expansion of the determinant around the identity, which means that this will be 1, the determinant of the identity, plus t times the trace of this. But the trace of that, since m is the trace of the transform is the same as the trace of the original matrix, is twice the trace of m times t, and the rest will be big O of t squared. And now if I take the square root of all this, which is the Jacobian, by another well-known Taylor expansion, this will be 1 plus the trace of m times t, big O of t squared. And what is the trace of m? If you look at it carefully, it's exactly the tangential derivative, the tangential divergence of v. Computed at x. Okay? So what do we get out of this? Now we finally, having computed the Jacobian, we finally compute this. Well, this will be the integral over sigma of the Jacobian, which is the integral of this. Now, the integral of 1 will give you the area of sigma. Well, big surprise. Then the integral of this will give you a linear term in t. And then the rest will be big O of t squared. And now if you ask, okay, what is the derivative of this at time t equals 0? Well, must be this. Huh? Sorry, without the t. Okay. Very well. We are not yet finished. So this formula is important because it tells you what happens to the area when you take a small infinitesimal deformation, right? And but we need a specific case which is particularly interesting. So forget about the proof now. Okay, this proof, it's not really a detailed proof, right? But you can make it correct. What do you have to assume? Something about the regularity of the surface, say it's C1, that's fine. Something about the regularity of the vector field, definitely, that has to be C1. But about the surface, honestly, the fact that it is C1 is not so important. What is important in all this proof is that it is contained. So sigma has to be contained into a C1 surface, okay? So actually it doesn't need to be a surface with, nice boundaries, so to speak. It's enough that the surface is, that sigma is a subset of a C1 surface. Then everything works fine, okay? Which for those who somehow already know what I'm talking about means that this formula works also if sigma is a rectifiable set, basically. Doesn't require a very regular sigma, but it requires some kind of, because in all this definition we don't use much about, so the formula in some sense, let's point out, rectifiable set will come out next lecture and will come out in other lectures. So what formulas you can extend from surfaces to rectifiable sets? Basically, rule of the thumb is every formula which does not require an integration by parts. Okay, but this doesn't require an integration by parts, we didn't need, so it extends from sigma to subset of sigma and then to rectifiable sets. Okay, formulas which requires integration by parts are delicate, but this is not. Okay. Yes. Let's go on. Let's make this formula more specific. And let's consider the case where the initial velocity is a normal vector field. Okay. Unit normal. Okay, so we assume for the time being that our points start moving orthogonally to V. Okay, in this case the formula becomes interesting because the tangential divergence of V is equal to alpha times the tangential divergence of eta. Which at first one might say there is something slightly wrong into this. I have the product of two functions. I take whatever is, it's a derivative, but only the derivative of the second term appears. But the reason, if you want, is that, well, let's say you do the computation in a formal way, but the reason is the following. You take the scalar product of this operator times this vector field, then apply the usual rule. You take the gradient of A times the normal plus the gradient A alpha, times the gradient, the divergence of eta. And this is 0 because of orthogonality. Okay? So the tangential gradient of alpha is, by definition, orthogonal to the normal. Whatever that means. So you find out that there is only, the formula is this one, which means that the first variation of the area is the following. Is the integral of alpha times the tangential divergence, of the normal vector field, and, well, this is known as the mean curvature. Let me quickly remind you, well, let's be a bit more precise about this. Okay, sometimes, well, that's exactly the definition of the mean curvature, so there is nothing to add if you take this as definition of mean curvature. So this is the mean curvature of sigma. If you take the classical definition of mean curvature, you start from second fundamental form. Let me see. Okay. Yeah, maybe it's better to explain. So if you have a surface, sigma, you fix a point, x, and you take the tangent plane. Okay, so let's say that this point x bar is the origin, just to avoid confusion. Then in some sense, you can always view your surface as a graph of a function over the tangent. Okay, this function will have value 0 and 0, will have derivative 0 and 0, but will have a possibly a non-trivial second order expansion in 0. What is a second order expansion? Taylor expansion is a quadratic form. Okay, it's a quadratic polynomial. Okay, this quadratic form is the second fundamental form. Okay, so view sigma as function graph of f from the tangent into the normal, and then it will have the second fundamental form of the surface sigma at this point x bar is just the second order term in the Taylor expansion of f at 0, which is a quadratic form, okay, a bilinear symmetric form. So second fundamental form at x, second fundamental form of sigma at x bar, which in this case is 0, is by definition, well, one of the definition is the quadratic term in the Taylor expansion of f at 0 equal x bar, okay? So it's a quadratic form on the tangent with values in the normal, okay? In case we are codimension, okay, in case we are codimension 1, so this will be T orthogonal. Okay, if you are in codimension 1, this is a linear space. I mean, it's you identify with R. So the second fundamental form is a real valued quadratic form. And here is the key identity, is that the differential of the normal. So now we go back to the codimension 1 case. The differential of the normal is exactly the second fundamental form. The differential of the normal at 0 is the second at x bar is the second fundamental form. Okay, so the differential of the normal, what is it? Okay, the normal is a map from the tangent, the normal is a map from the surface to the sphere. Its differential is a linear map from the tangent to the tangent, because the tangent at the sphere in a vector is exactly. So its differential is a linear map from the tangent to the tangent. But every quadratic form is represented by a linear map. Okay, so I'm associating to this linear map its quadratic form. Okay, so this is the basic identity, which, given this representation, you can prove in a few seconds if you take time. Take the usual formula for the gradients. So the normal is minus the gradients of f comma 1. You do the computation and you get this formula here. But then, of course, the trace of this is exactly the trace of this one. Okay, but the trace of the second fundamental formula is the sum of the eigenvalues, which is the mean curvature, if you want. That's the usual definition of the mean curvature. Sum of eigenvalues. And the trace of the differential is the divergence, the tangential divergence. Okay, so this is the basic identity you can prove by yourself if you want to do a little of it. And so this is the mean curvature, okay? And now I think it's time to finish, sum up. We are almost there. Okay. Okay, now so we start talking about surfaces which minimize the area. Okay, so far we were just talking about surfaces and the formation of surfaces. Now we consider from now on and for the next 10 minutes, maybe less, sigma minimizes the area, the volume, among all surfaces with same boundary. And, well, again, codimension 1. Because I'm going to use the formula before, that only works in codimension 1. Okay? And then the statement you have is, okay, lemma. Well, the lemma says that since it is a minimizer, then the area of this must be larger than the area. Okay, this is classical calculus of variation right now. Just to recall, the area of this must be larger than the area of sigma, so this derivative has to be positive. Okay. Well, for every family of deformation, for every flow which is admissible, well, what are the admissible flows? Okay, how does the argument run? I'm saying that the area of this surface must be larger than the area of sigma, right? Because what? Because sigma is minimizing the area, yes, but only among surfaces with the same boundary. So I have to make sure that my flow, that these surfaces sigma t have the same boundary as sigma, right? Otherwise I can't apply this minimization argument. So I can only consider flows that leaves the boundary of sigma untouched. Okay? Otherwise I'm changing the boundary of t and I cannot claim that any minimality in this larger setting. Okay? So flows, I can only consider flows that leaves the boundary. So what I get, but this is, I recall, okay, now I say that this implies the following. Okay, so this said there is nothing to be proven, okay, right? It's obvious, self-evident, I hope. Okay, so now I claim that then I claim that the integral of alpha times h over sigma is larger or equal than 0 for every alpha scalar function which is 0 on the boundary. Okay, how do I go from here to there? Well, we're almost there. One say, well, we can consider vector field, flows whose initial velocity is normal. If we consider those flows, certainly the first variation of the area is given by this formula. Okay, this is just the okay, and so it is this formula here, right? It's a special case of this formula, where I restrict myself to flows with initial velocity orthogonal to sigma. But not exactly, because I'm saying here that I can do that for every alpha, regardless whether it comes from a flow or not. So the question is, given a positive function, a function which is 0 on the boundary of sigma, do I have a flow for which alpha eta is the initial velocity. So that's the only thing I have to prove, because I'm not saying every alpha that comes from a flow, I'm saying every alpha, okay? So it's a triviality. So proof amounts to this: show that for every alpha as above, there exists a flow such that the initial velocity is alpha times eta. Do we have it? Yes. Take phi t of x, just x, plus alpha of x, eta of x, times t. For t sufficiently small, this is a flow, okay? And since alpha is 0 on the boundary this will be 0, so the points on the boundary are left untouched, okay? And now we are finished, because a corollary of this because you can change sign to alpha, okay? So it has positive, you take minus alpha, it's still a function, and you get, okay? Triviality, but let's just specify it. Okay, but then this is a usual lemma, right? If you have a function which multiplied for any test function, 0 on the boundary, doesn't matter, gives 0 as an integral, then this function has to be 0. Okay, which is exactly the mean curvature equation. Okay? So, right. Perfect. I think there is not else to be mentioned except one thing. So far, so good. One would say, well, it's clear that how we pass from here to here, we restricted to a subclass of flows that is the normal flows, okay? And then one might wonder whether in doing this we are losing information. That is, well, certainly this is the best information I can obtain about the minimality of sigma. I mean, being minimal, if I translate the fact that sigma is minimal in terms of infinitesimal information, I get this one, nothing better. In the moment I pass from this to this, I take a subset of this information. Am I losing something? Maybe that not only surface of minimal area satisfies this equation, but something else. After all, and the answer is no. In some sense, the vice versa is true also in the smooth case. That is, it appears like we are losing some information, but it's not true. Now, without making it some abstract statement, okay, the abstract statement being that these vector fields, normal vector fields, generate the tangent space in the manifold observed, blah, blah, blah. But in a more concrete way, if this is your sigma, and this is your sigma t, obtained by any flow, so let's say that the flow is not orthogonal, well, then the same sigma t can be also obtained by a normal flow, okay? So what I mean is that the fact that these points, instead of moving normally, moves in a slanted way, is not important, as long as we are considering the area functional, right? So basically, this is saying, take it as it comes, that restricting to normal vector field doesn't mean loss of information, okay? So this statement looks stronger than that one. In fact, it's equivalent, okay? Okay, so this is it for today, and thank you for your patience.